Hello, everyone. Welcome to today's webinar on big data, fast data, the need for in-memory database technology. My name is Peter Vescuso. I'll be the moderator and one of the presenters today. A couple of housekeeping items before we get started. Usually everyone wants to know about getting the slides in a recording. You'll all get that in an email, typically about 24 hours after the webinar is concluded. Also, this is a live presentation, and you can't see the other attendees, but there is a lot of people on the call. So, it's not an open line. We would like to encourage you to ask questions and use the chat window that's on your screen, which I believe is on the lower right. The lines are muted, and we'll, like I said, take questions through the chat window, and we'll try to answer those at the end of the presentation. With me today presenting is Mike Stonebraker. Mike is a professor at MIT. He's also co-founder of VaultDB, but he's co-founded many other companies. He was one of the original architects of Ingress, Postgres. More recently, he's been the chief architect and founder around the stream processing technology, which got commercialized as Streambase, then a C-store column-oriented database commercialized as Vertica, the H-store transaction processing engine that got commercialized as Vault, and he's working on a number of other database technologies more in the science and search field. But we're really excited to have Mike with us today. I'm Peter Vescuso. I head up marketing at VaultDB. And I'll be one of the presenters. I'll basically do some context setting at the front. I'll then turn it over to Mike, and Mike is going to go into detail about our database architecture. Okay, so with that, let me just quickly, I just talked over the overview, talk a little bit about fast data, which we view as kind of a new emerging segment, kind of the new big. The corporate data architecture and how that's evolving. Then I'll hand it over to Mike, and he'll talk about the specifics of the database architecture and why it's important for using the right database for the job. And then we'll come back and talk about why VaultDB is a terrific answer for streaming data applications. But to set the scene, just want to talk through a couple of scenarios. This is a picture of a shopper, and this is kind of the state-of-the-art of recommendation engines. The suggestion here is that for this woman who's shopping, customers who bought bananas also bought this collection of other things that are closely associated with it. Now, in terms of this recommendation, it's timely. The woman's shopping, so that's good. But it's not necessarily accurate or personalized to this particular shopper. She could be shopping for bananas to make a cake, to make a banana split, or some other context. And the recommendations here, which are typically pulled out of a data warehouse and usually not in real time, are not exactly kind of matched to her needs and her specific situation. So that's one example. Taking a look at another example. This is a picture of a miner holding a canary. So you've heard about the canary in the coal mine. The interesting aspect about this application is the canary is a huge ingester of data, processing it in real time, and the miner's actually able to kind of watch that and discern kind of what's going on and figure out if there's a problem or not. But today's mines and miners are being outfitted with all kinds of sensors and technology to assess things quickly in real time, and there's a need now to be able to process that data, do intelligent transactions on that data to see what's going on. Could be that a miner is, sensor on a miner is picking up, say, CO2 that they're exhaling, and it could be just the status of one individual miner, and you might want to know whether that's really a problem that's affecting all the other miners in the vicinity there, so you might need to do a transaction, collect and aggregate the data from the other miners, and then take action based on whether you think that's a problem or not. So those kind of situations are examples, these scenarios are examples of the opportunity to take advantage of things that are happening in real time from streaming data. And that's kind of a different setup and paradigm from a lot of the kind of big data work that's been done in the past. This is a picture. I think this is the kind of picture that, I think it will annoy Mike. Mike really likes detail and specifics and architecture. But this is a picture that I like to use, being the marketing guy, to illustrate, we talk a lot about big data and the data lake. And to really highlight the difference between that and streaming data flowing in real time, the data lake is full of data that's been saved and stored. And then you're going back in time and forensically looking for value, trends, et cetera, to pull out of that. Fast data or streaming data is data that's flowing in real time. And I think the analogy to talk about kind of potential energy of the data, as in the potential energy of data coming over a waterfall, is not too far stretched. That potential energy has value only as long as the data is moving. Once it's saved and stored, you can still get value out of the data, but it's a different type of analysis and a different type of an opportunity. Or put in a little more structural way, we're talking about fast data being the velocity side of big data. If you're working on a data pipeline, data is flowing in rapidly, it's being ingested, typically exported and put into a big data system. But with today's systems and technology, there's the opportunity now to do things in real time processing, and extract more and more value out of that. Okay, so fast data, as I said before, potential energy, a lot of the value out of the moving data is gone once it stops moving. A shopper recommendation, the ability to detect if there was a problem with the miners in that mine, if CO2 levels were rising. Online game engagement and interaction. You got to know what's going on with the game while it's happening. I noticed, I think it was yesterday, Microsoft purchased this company, Minecraft, for $2 billion. And there's some sense in reading the coverage of that story that this kind of engagement and personalization isn't just going to be for games. It's going to become more and more important in terms of organizations, companies engaging with their customers. If you're trying to prevent a denial of service attack, you need to do that in real time. Identifying a fraud, you want to do in real time. And basically, you lose value if there's an event that has potential in the moment if you're going to store it and try to extract value later. Kind of the business way of saying it is that there's competitive advantage in being able to tap into data, get instant insight, action, and awareness, and do something with it in real time. I think there's some sense out there that there's really a trade-off that's required between doing things with data that's fast, being able to sample recommendations, knowing that somebody's walked into a store because of their device, or that there's some fraud issue going on. But the trade-off is being able to kind of know some things in real time versus actually being smart about what's going on, using context, using personalization. So sampling recommendations, making aggregate assumptions about things, and making suggestions after a purchase, there's value lost. For a lot of organizations, companies in the advertising business, serving up an ad might be served at the right time, but if you're serving it when the budget has run out, that can be a problem. Knowing that context and state of affairs at the moment is really important. Finding a fraud out days later can help, but it's certainly much better to know it in real time. So there's kind of, I'd suggest a false trade-off between doing things with data that's fast and doing things with data that's smart. Now, the good news is on the analytics side and the investment that's been pouring into big data, the analytics stack is really taking shape around the data lake. All kinds of terrific applications are being developed around business intelligence and reporting, being able to do SQL on Hadoop, doing exploratory analytics, using batch manipulation and pre-processes, things like MapReduce, are ways to add value, get insight into the data that's been stored. And the enterprise applications are also feeding that data lake with the flow out of them and incorporating them into the data lake to get the potential value that sits with those into the analysis stack. But what we're talking about is if there's opportunity and value in analytics, isn't the point about making better decisions, better personalization, better detection? And if there is, why is there necessarily a trade-off between being able to do things fast, do them smart, and take advantage of the opportunity that exists? Applications, our view is applications in analytics traditionally have been developed separately, but in today's world, that's really not the case. They're really being designed together, and it's driving a set of new requirements for corporate data architecture to be able to accommodate both ends of the spectrum here, both fast data as well as big data. And to illustrate that, talking about the requirements involve being able to ingest huge amounts of data that are being generated from all kinds of events, social media, machine to machine, Internet of Things, all kinds of different applications that are driving data. Being able to make data-driven decisions on those events and being able to do it on a per-event basis is all about taking data that could be considered dumb, adding intelligence to it, making it smart, and getting more value out of it. Being able to analyze in real time to get visibility into operations. And I think that is one of the big shifts here in terms of applications, being able to add value to operations as they're running. So systems need to be able to support that, and there's a corporate data architecture that we think is evolving that we'll show here that can make this much more viable today. So in terms of where do we see the future of corporate data architecture, we talked about the big data side of things, the data lake and the applications that are being designed around it. If we look at the requirements of processing the fast data, making it smart, this is the beginnings of what that architecture looks like. Having the capability to ingest data in real time, make decisions on it, do real-time analytics, and then eventually export that data to the data lake, whether that be Hadoop or other OLAP stores, is what the architecture looks like. And then being able to leverage the big data side, those arrows that popped up show the ability to tap into the value that sits there, add intelligence based on historical trends to do an even better job on the front end so that you can make the real-time analysis even more valuable. So that's what we see as the corporate data architecture. And today, using a fast operational database is one of the ways of making this a reality and being able to do things that have traditionally not been possible because databases in the past were not fast enough, didn't have the speed, didn't have the in-memory performance. And today, you can do all that. You can know what the current state of things are. You can do transactions in real time on a per-event basis and be much smarter about the decisions and the analytics that are being done. So that's our view of what the corporate data architecture looks like. Mike Stonebraker has been saying for years architecture is important. He's also emphasized for a long time that specialized databases are really what you need for the different opportunities that exist in the enterprise today. And I'm going to turn it over to Mike here to kind of take it over and talk about the database architecture that supports this fast data architecture that we've just presented. So with that, here's Mike Stonebraker.
Thanks, Peter. So I'm going to talk about sort of the back end to the kinds of applications Peter was talking about. I just want to call out ad placement. Say if you're going to put an ad on somebody's web page, you have to do that in milliseconds. You've got to be able to personalize that ad for the actual consumer, which means you have to look up what his characteristics are. You also have to look up the budget of any given advertiser, and so there's a database behind ad placement, and it has to be blindingly fast, basically millisecond response time, small numbers of milliseconds. Let me just give you one other quick application. There's a very large electronic Wall Street style electronic trading firm. They have electronic trading desks all over the world. For example, Tokyo, Singapore, New York, and so forth. And they are doing electronic trading at millisecond speeds. The CEO of the company wants to maintain the global position of his company for or against every single stock on the planet in milliseconds, and be able to pull the plug if his risk profile gets too high. You cannot lose messages. This is a never lose my data kind of application at blindingly high speed, and again having to keep track of a fair amount of stored state. So fast applications of this sort which require a database behind them. So I will talk about how to do that, and then at the end I will talk a little bit about the particular characteristics of streaming data, since both of these applications in fact are driven by messages that are coming in off the wire. So let's start with the what's the traditional way of doing databases? Well, you go call up your Oracle salesman. He tells you that Oracle 9i or 10G or 12H is the answer. Now, what was your question? So the elephants, the major vendors, say one with 3 letters in the company name, one with 9 letters, and one with 6. And these are disk-based database systems that have been around more than 20 years. And unless you squint, this is what they look like. They store fields in one record contiguously on disk, not in main memory, on disk. B-tree indexing is the gold standard to get at your data. They store data in disk blocks that is, heavily encoded for some very good technical reasons. They often align fields on byte or word boundaries to save CPU time. And they are using technology to do queries and updates that dates from the 1970s. In the 1970s, there was a huge argument about how to make sure that you could do transaction processing correctly. And the technology that was agreed on was what's called row-level dynamic locking. That's what's in all of the current elephant systems. And in order to recover from crashes, you have to write footprints out into a log. And so there's a standard technology for doing write-ahead logging. And this is what you get when you buy a disk-based database system. If you can just go forward a slide. I will just call that a row store. This exemplifies the elephants and MySQL, Postgres, ... Essentially, all database systems on the planet are disk-based row stores. So I now want to tell you why you should not be interested in any of these products. Next slide. So the first reality check, which is, I think you have, if you have to sort of buy into, is that main memory is getting really cheap and really, really big. So the sorts of databases we're talking about are not that gigantic. A terabyte is a really big database for this style of application. If you want to buy a terabyte of main memory, you do not need a very big checkbook. Less than 30K will be happy, many vendors will be happy to sell you a terabyte. So if you have a database that's in the gigabytes or small number of terabytes range, you are a candidate for main memory. Now I know that the most difficult database on the planet, that is updated a lot, is the Facebook social graph. Facebook has the most difficult database problem on the planet, in my opinion. That's an outlier. Most of you don't have petabyte-sized transaction databases. So you should think main memory. Next slide. In a main memory world, you've got to worry about overhead. So the way you interact with the elephant's databases is with something called ODBC or JDBC. And that's a very heavyweight protocol that dates from the 80s, and it's way too heavy to be fast. You need a lighter weight protocol, and anyone who tries to sell you an ODBC or JDBC interface, you are not going to be happy. So you need a lightweight way to get transactions into and out of your system. There are a bunch of techniques that have been developed, and you need to use a database system that uses them. Otherwise, the high pole in the tent, in other words, what will determine the speed at which you can do transactions, is the client interface. So, for example, Microsoft has just released a main memory database system called Hekaton. It's a part of SQL Server 14. Unfortunately for Microsoft, Hekaton is integrated with SQL Server 14, which means they have to use ODBC and JDBC. So the speed of Hekaton is completely determined by the speed of the client interface, and it's going to be slow, slow, slow. So the reality check number 2 is don't use ODBC. You've got to use stored procedures. You've got to use an asynchronous interface. You've got to use connection pooling. All of these words, if you don't know what they mean, it's time to learn. Okay, next slide. If your data fits in main memory and you're using a high-speed client interface, then you're up against the details of how to make database system backends go fast. So about 5 years ago, we ran the following experiment. We ran TPCC on a main memory data, on a disk-based database system in which all the data fit in main memory, which means the data is in your buffer pool in main memory, but it's in disk format using a disk-based database system. We instrumented the source code. We used a database system called Shore, just because we didn't have the Oracle source code that we could instrument. And so all of the elephants would be expected to have very similar performance. And here's what we found out, which is the useful work of actually doing TPCC, which is finding the records you want, updating them, and so forth, was way under 10% of the total path length. More than 90% was what you would classify as overhead. And the overhead was, roughly speaking, in 4 equal-sized buckets, which are large pie slices. The first one is managing the buffer pool, which is every disk-based system has one, which is the cache of disk pages that are in main memory. That's expensive for lots of technical reasons. You have to maintain data that's encoded. You have to decode it to actually use it. You have to maintain an LRU eviction order. You've got to be able to pin pages in main memory under certain circumstances. There's a lot of technical details, and the buffer pool is simply complicated and chews up about a quarter of the overhead. Dynamic locking chews up another quarter. Whenever you touch a record, you've got to set a read lock. Whenever you update a record, you've got to change that read lock to a write lock. Managing the lock table is another overhead-intensive operation. The third one is performing a write-ahead log, which is required for crash recovery purposes, is another expensive piece of overhead. Whenever you update a record, you've got to write the before image of that record, the after image of that record into a log, and you have to force that log to disk at commit time. And so those three things are just expensive. The fourth one requires a little bit of explanation, which is all database systems, or all traditional database systems of the row store variety are multi-threaded, because you get bunches of CPU cores these days, and so you have multiple threads alive doing database processing on the same database. Well, the problem is that database systems have a large amount of shared state. For example, setting a lock in the lock table is updating a piece of shared state. You can't have multiple CPU counters pawing around in the lock table simultaneously without the danger of corruption. So if you are going to run multi-threaded, you have to set what are called latches around the shared data structures, and that makes threads wait. And so the latching requirements are another big piece of overhead. So that's where all the time goes if you run a traditional disk-based database system. And you can see that useful work is a very small part of the total amount of time. And because of these four big pie slices, disk-based database systems are slow on transaction processing. If you need to do 30 transactions a second or 30 messages a second, by all means run one of these heavyweight disk-based systems. You could equally well run 30 transactions a second on your wristwatch. And so if you don't need to go fast, it won't matter. But if you want to go fast and produce millisecond response time, then you've got to worry about these four pie slices. So the first thing, which should be pretty obvious to everybody, is that if somebody comes and tells you that they have a better B tree and they will thereby be able to find your records faster, that's going to make very little difference, because that only affects the 4% piece of the pie. It doesn't affect the other 90+%. So it's irrelevant. So if any company comes to you and says, I have better data structures, they're going to accelerate your application. They're not going to accelerate your high velocity applications. Next slide. So to go fast, it's pretty clear that you have to get rid of all four pieces of this pie. Anything less is not going to go fast. So my favorite example is of course, Oracle's Times 10. Times 10 is a main memory database system sold by Oracle. It's been around for more than 15 years. It is a main memory database system, so there is no buffer pool. However, they use row-level locking. That pie slice is right there. They use a standard write-ahead log. That piece of the pie is right there. And the system is multi-threaded, so that piece of the pie is still there. So one slice out of the four is gone, but three slices remain. So let's do a little back of the envelope calculation. which is if you run just a vanilla elephant system with all 4 pie slices present, you'll go at, say, unit performance. So that's just, let that be whatever it is. If I can get rid of 1 pie slice, well, then I have 3 of them remaining. I've gotten rid of 24% of the overhead, but 72% is still there. So I go faster, but my speed up is much less than a factor of 2. If I get rid of 2 pie slices, I go about twice as fast. If I get rid of 3 of the 4 pie slices, I go faster again. But the only dramatic win comes if I get rid of all 4 of them. So anybody that doesn't get rid of all 4 pie slices is going to lose. So let's look at these slices one by one. So the first thing is you have no chance of going fast if you don't get rid of the buffer pool. No chance whatsoever. All the NoSQL guys are disk-based database systems. They all have a buffer pool. They are all going to lose. All the elephants, MySQL, all the disk-based traditional database systems are going to lose. You've got to run a main memory database system or you lose. So think main memory, because that's the way to get rid of the buffer pool. But that's only the start. You still got 3 other pie slices you've got to get rid of. So let's look at these one by one. So a database system has lots of shared data structures. I mentioned the lock table. B trees are another shared data structure. You've got to write data into a write-ahead log. The head of that write-ahead log is a shared data structure. Sorting buffers, malloc memory, so forth and so on. DBMS has lots of shared data structures, all of which have to be latched. So in a multi-core world, you need latches to avoid corruption of all of these shared data structures. So, and it's just going to get worse because Intel is giving us more and more cores on a chip. And this, once you get more than, say, 8 cores on a chip or maybe 16, the latch overhead starts to kill you. And we've seen simulations that say nobody is going to give you very good performance in a multi-threaded world above 64 cores on a chip. So this is going to be a growing problem. So you've got to solve it, because that pie slice will kill you otherwise. So the Volt solution is we use single-threaded code. Volt is not multi-threaded. If there's a big overhead to shared data structures, then don't use multi-threading. Figure out how to go fast without using multi-threading. The only other alternative is to use what are called latch-free data structures. There's quite a bit of research in this area. So far, it's been mostly focused on B trees and on concurrency control, and all the other data structures in a database system would have to be included. So I'm not saying you can't do it this way, but anyone who's multi-threaded has a lot of work to do to try and knock down the size of this pie slice. And the obvious way to do it is to use single-threaded code, which is what we do right now. We get rid of this pie slice completely. Next slide. So now we've talked about 2 of these pie slices. The third one is, how about a write-ahead log, which is you have to write the before image and the after image onto disk and make sure it's committed before the transaction completes. So what we did was an MIT graduate student named Nirmesh Malvaiya implemented the standard write-ahead logging scheme in VoltDB. So that's option A, which is just implement vanilla write-ahead logging. you should realize that the minute you do this, that pi slice comes right back and it's going to bite you. And we compared it against the current Volt DB scheme. And what Volt does is we do asynchronous transaction consistent checkpoints. So we checkpoint the data to disk, but asynchronously and not coupled to transaction commits. And then we log the command that you're running, not the data effects of that transaction. So if you go up to McDonald's and you order a number 6 with a Diet Coke and fries, we log 6 Diet Coke fries, not the data records that get impacted by that transaction. So command logging logs just a little bit of stuff rather than a lot of stuff. That will knock the size of the pi slice way down. So since I'm the techie, I have to give you some graphs. So the next 2 slides have graphs in them. And so what this shows is transaction throughput on TPCC on the vertical axis versus the speed that you're trying to go. So if you don't want to go fast, it doesn't matter. So you want to look over to the right-hand side of this graph. And the bottom curve is what you get in Volt if you add standard write-ahead logging. So you can see that the performance peaks out at about 500,000 transactions per second. However, the top curve, the top solid line curve, is what command logging gives you, which is it peaks out about 50% higher. And it's almost as high as the dotted line, which is no logging at all. So if you're very smart about the way what you log and how you log it, you can get that pi slice to be very small, but not the way that the traditional elephants do it. Next slide. Now, of course, there's a cost to doing command logging, which is if the power goes out and you have to recover your database, then what we have to do in Volt is replay your transactions. That number 6 fries and a Diet Coke, we have to actually run that transaction at recovery time. In contrast, the write-ahead log guys only need to install the after images of the data, which is faster. So the recovery time, which is on the vertical axis, versus how fast you were trying to go. The bottom line is us, which is how fast we can recover. The top line is how fast you can recover with the traditional technology, and they can recover about 50% faster than we can. Next slide. So basically, the bottom line is at runtime, we are 50% faster than if you use data logging. And at recovery time, we're 50% slower. However, I got to remind you that Volt automatically gives you high availability with replication. So the only time you ever have to stop and recover is if you get a cluster-wide failure of some sort, like the power goes out. This happens every few months, not every few minutes. And on all the other kinds of failures, Volt automatically fails over to a backup and just keeps going. So the question of the day is, would you rather have 50% better performance at runtime in exchange for every few months it's going to cost you 50% longer to recover from a catastrophic failure? It's a no-brainer to say I'll take runtime performance. So Volt is completely engineered to go fast at runtime, and the trade-offs are invariably things like I just described, which is every few months, if you actually have to stop and recover, we are going to take a little bit longer, but we are optimized to give you blindingly fast performance at runtime. Next slide. The final slice of the pie is concurrency control. Nobody who wants to go fast is using traditional dynamic logging. It's just too slow. So what Volt does is a sophisticated timestamp ordering scheme. There are other possibilities. Hekaton uses multi-version concurrency control, and there are other very lightweight ideas that have been investigated recently, but you cannot do row-level dynamic locking. It is just too slow. So next slide. The net on database systems is that the way VoltDB does things is we have one deterministic concurrency control scheme which allows you to do high availability the way we do it. We use command logging, which is 50% faster. We have a high availability replication scheme, which is very tricky and depends on the active, the primary and replica databases being updated in the same order, and that gives you another big performance boost. So we are very clever on the way we do all of the pie slices. The net is we give you a main memory database system that is pure ACID. It supports pure transactions. It never loses your data. And anything you read about the products from the elephants, and essentially all the database textbooks, are basically obsolete. They are just way too slow. And the summary is on the next slide, which is on TPCC. We are about 100 times faster than the major elephant products. So the way to think about this is that you can have millisecond response time from us. You can have second response time from the elephants. You can run us on 2 or 3 nodes. You can run the elephants on 200 or 300 nodes. Which would you rather do? The reason we are 100x the elephants is that all 4 pie slices are either gone or wildly reduced in size. So if you care about performance, come and see us. Next slide. So now I want to talk briefly about the aspects of streaming data that are important. So my favorite example is multiplayer internet games. The son of one of my friends is really into World of Warcraft. I can't see why he is so interested, but he is. And so if you want to find all the players that are shooting and moving in the same 1-second window, what you're looking at is the stream of actions and trying to find patterns in that stream. And complex event processing systems are very good at doing pattern investigation in streams. Next slide. However, a second multiplayer game example is, suppose I want to keep the leaderboard for this game, which is I want to, for any given interesting metric, maintain the 25 best players in real time. And by the way, make sure the leaderboard is correct, which means don't lose any of my messages. If you want to do this application, then you need a transactional database, and you've got to use a database that can keep track of your state accurately, correctly, and fast. So this is a sweet spot for VoltDB. So if you're trying largely to maintain state at very high speed, then run something like Volt. If you're looking for patterns in a database, then the CEP products will work out well for you. In my opinion, most of the applications I see need to reliably maintain state, which makes CEP products basically not applicable. So VoltDB is very good at the streaming applications that require you to maintain state. So if you have streaming data, we are absolutely happy to process it. We transactionally process messages. Every incoming message becomes a transaction. We never lose your data, and we never lose your messages. You can run normal SQL queries on your data. In the electronic trading example, if you want to find the enterprise-wide position on IBM, we're happy to do that. If you want to run windowing operations, which is find me the 1-minute moving average of IBM's stock price, we're happy to do that. So we have all the capabilities you need to operate on streaming data. And the sweet spot of what we're good at is if you have to maintain reliably, state in this world. Next slide. So on streaming data, it works fine on VoltDB. You can go as fast as you need to go. Just add more nodes. VoltDB scales linearly. We've never seen a streaming transactional problem that we couldn't solve, which is you run out of ability to generate messages long before we run out of the ability to process them. So from my point of view, if you have a streaming application, look at whether you need to reliably maintain state. If you do, you need us. If you don't need to reliably maintain state, then there are a lot of solutions you can apply. That's the end of my slides. Somebody, namely marketing, put some stuff here at the end.
Marketing, Mike, this is data. Data. So wanted to show, and there were a couple of questions about running VoltDB in the cloud. By the way, if you go to our website, you can run VoltDB in the cloud for free, but you do have to use your own Amazon account. You go to the website, it says try VoltDB now. There's actually a couple of choices there. You could download the code and run it on your own enterprise server. You can run it in Amazon. We've got it set up with CloudFormation services to make it easy, so you can test it out there, and that's all for free. And speaking of cloud, we've recently run this industry benchmark, the Yahoo Cloud Services benchmark, which is a very popular cloud-based benchmark. We ran it on Amazon. We're showing workload B here, which is 95% reads, 5% updates. It's one of the most widely reported. And you can see in the chart on the right the kind of nice linear scalability going from 3 to 6 to 9 to 12 nodes, with up to, at 12 nodes, hitting 724,000 transactions per second. Of all the data that we've seen, this is the best performance where it's actually run in the cloud. Other companies may run it on their own servers on-prem, but this is the fastest performance in the cloud, and by the way, running in a virtualized environment. So we're pretty excited about that. Mike set out to architect the fastest database in the world, and we think we've got it here. But it also gets better than that. So that's on Amazon's virtualized environment. We recently reran the same benchmark, and this is on SoftLayer's bare metal servers. SoftLayer is an IBM company. They offer virtualized environments, but they also offer bare metal servers, which allows you to take advantage of cloud infrastructure and run applications that are performance-oriented without the overhead of virtualization. So same benchmark, same run, and the performance here. Now, again, the virtualization layer is not present. It's running on bare metal servers. Much higher performance, peaks out at 12 nodes at 2.4 million transactions per second. So that's 5x the performance of the virtualized benchmark that we ran. So we're pretty excited about that. And as I said, if you want to test it out, just come to the Volt website to do it. So we've been talking about speeds and feeds and architecture. I did want to take the opportunity to talk about all of this. The purpose of all this stuff is to deliver business advantage. And I said before, our view is fast data applications are growing. organizations are figuring out how to tap into data in real time. There's tremendous value in that. It's a different opportunity, and they're deriving enormous value out of it. So here are some examples. Sakura Networks, who's the largest ISP in Japan, uses VoltDB to prevent denial of service attacks. They actually inspect every incoming Ethernet packet, and they're checking IP addresses, and they're figuring out what's friendly and what's faux. And what they've been able to do is discover 100% of denial of service attacks in real time, and they've improved their response time by 97%. In the past, a lot of this was not possible in real time, and they typically have to have human intervention and could take up to an hour to respond. A communication service provider, Novotel, uses VoltDB on their existing network infrastructure. We're able to increase the throughput and utilization by 150% by just switching over to the performance they get out of Volt. Online game analytics. This is Delta DNA. We did a webinar with them a month ago. We've got a terrific video on our website from Chris Wright, their CTO, who talks at length about how they use the performance of VoltDB to, Mike was talking about his friend who's a gamer. These guys are powering games that have millions of users engaging in real time, how they use VoltDB's performance in real-time analytics to increase engagement and ultimately increase conversion rates, because that's how they make money, getting players to convert from the free to fee-based business. And they've been able to increase conversion rates by 30% with the high-speed analytics that they're using. Mobile network management. This is a customer of ours who's been able to improve their overall performance, simplify their infrastructure. They've totally eliminated the storage area network that they were buying from a large popular database company that cost on the order of $500,000, and have been able to deploy a solution now that has unlimited scale and can be deployed in the cloud. Mobile ad service provider, customer of ours who's been able to reduce their operating expense by cutting the number of servers required for their business from 100 down to 7, and reducing latency and eliminating those ad budget overages I mentioned earlier. So some real-world examples of delivering competitive advantage by using modern in-memory database technology. There's lots of these fast data problems out there. There are many in the Internet of Things space, and with energy and smart grid, smart meter applications, in personalized targeting. We talked about that earlier. Online shoppers, but virtually every enterprise out there that's serving consumers will have mobile applications where they're trying to maximize and optimize their customers' experience and make it more personal and engaging in real time. Mentioned telco. Mike talked about capital markets. I think you can appreciate they've always appreciated performance and real-timeness for doing transactions, but also for doing risk management. And we've talked about a couple of kind of infrastructure examples of being able to improve utilization and overall network performance. So that's the presentation. We're going to take questions. There's a bunch that have come in. I did want to give a quick shout out and thank you to the Association of Enterprise Architects and Birgit Hartje for supporting us in putting on this webinar and giving us the opportunity to talk about what we think is some valuable technology. So quickly on questions, because we only have a few minutes left. Mike, there were still a lot of questions about the traditional databases. I think you by and large talked about it, but the question was like Oracle, Microsoft, SAP, HANA. They've all moved to in-memory, so they obviously can handle these fast data applications now, right?
Not quite. So let's start with Microsoft. So Microsoft has a DBMS hackathon. It comes with SQL Server 14, it is not going to be particularly performant because it's forced into the infrastructure of SQL Server 14. So by all means, we'd love you to bake off Hackathon against us. So that was number one. Number two was HANA. HANA, is a work in progress. Their decision support version of HANA seems to be executing. Their transaction version of HANA is still future tense. So it's impossible for me to comment on transaction processing HANA because it really doesn't run yet. Oracle has an in-memory option which is distinct from times 10. Times 10 has a performance problem. Please benchmark us against times 10. We would be delighted if you did that. Their in-memory option turns out to be integrated with their conventional disk-based DBMS. So it will run, it's a caching system that will cache historical data so that you can run decision support queries on it. In an update-oriented world, Oracle cache will make no difference whatsoever. So we absolutely love you people to benchmark us against Oracle. As I say, my favorite Oracle statement is that on what hardware platform does Oracle run the best? The answer is a 35mm slide projector. So always take anything that Oracle marketing says with a grain of salt. When Oracle has a problem, they turn their marketing people loose. When we have a problem, we turn our technical people loose. So those are the three examples mentioned. IBM also has a main memory database system called SonicDB. It only runs on a single node, so it will not scale out. But I think the proof is in the pudding, which is if you want to go fast, take a look at all of the options, and we expect that you will come choose us.
Okay, and then kind of related to that, how much do solid-state drives help traditional database performance?
The answer is not very much. The reason is that will knock the latency down of getting data off the disk. However, the pie slices I presented you was assuming all the data fits in main memory. In other words, you're never reading and writing data off the disk. So a solid-state disk will help. It will help a disk-based system go somewhat faster because writing the write-ahead log will go faster, and whenever you have to get something off the disk, that will go faster. So it definitely will win, but it isn't the game changer that running something like Volt is.
Right. Thanks. There was a question. How does VoltDB compare to MemSQL? We're almost out of time. I'll just say quickly. Our view is MemSQL is basically an in-memory OLAP technology. They don't support things like multi-statement transactions or stored procedures. So we think they're actually in a bit of a different category. Another question where, can you mention any medical application use cases? I'll mention three quickly. One is remote monitoring of patients wearing medical devices, for example, when they go home, to examine trends and looking at the data that's being produced to look for problems in real time. Another one that's that's a medical one is real-time signal processing, inspecting SIP packets to be able to help people with hearing aids that have certain hearing problems and optimize the signal for the type of problem they have. And then this one is really more logistics in a hospital, real-time tracking of equipment, where it is in the hospital, et cetera. And with that, just on the slide here, we'd love you to try out VoltDB, as Mike said. We think the proof is in the pudding. Test it yourself. Download it, run it in the cloud. We'd love to help you do that. We don't think you need help, but we would love to help you do that or help you with any use cases that you have. So feel free to contact us, info@voltdb.com. And with that, we'll say goodbye. So thanks for attending and look forward to talking to you in the future.